Thank you everyone, and welcome to the VPEC webinar, the 13th. And the today webinar is very special because this is the first time we organize a webinar, a VPEC webinar, using only English. And the two presenters are foreigner, not Vietnamese. Usually we only invite Vietnamese speaker. So this is the first time two speakers are or not Vietnamese. So firstly, Professor Rakesh and Professor Liu is the first time to go to a VPEC webinar. So I would like to spend a few minutes to introduce our community. Our community called VPEC or VPEC, the Vietnam Power Electronics Community. It is founded on last year, May 29th, 2019 in Busan. So you may know about ECC Asia, ICPE, held in Busan last year. And at that time, we many of us Vietnamese scholars to attend the conference, and we decided to establish a community to talk and to discuss and to study and to share knowledge and wisdoms about power electronics. Then from that day, VPEC is founded. Then after more than a year, we have now 1,200 members. Then most of our members are students, Vietnamese, and students are studying in Vietnam, in UK, US, in many countries. And as I do some statistic, we have about 10 countries. Our members are in about 10 countries or even more. Then, okay, our mission, we have three main missions. Firstly, our community is to connect people, to connect scientists, universities, industries, students, etc. Then when we connect everyone, we would like to share our wisdoms, our knowledge about power electronics and the related applications. And after that, based on that community, we'd like to build like a friendship, build collaboration, communities, and we would like to contribute not only to Vietnamese technological and science development. We also want to contribute to the international improvement as well. Then this is our some of our vision. Okay, so I skip this. As for our activities, we have actually many activities, not only this webinar. Besides, we also organize a Facebook forum where we discuss, we share many lecture notes, like poster, etc. Then every month we have webinar, like we are doing this today. Then we also have many other activities like a conference. This year, we also organize in this conference ISPEC or ISPEC, the first international symposium on power, energy, and cybernetics. This will be held online due to COVID-19. Then you all, both Professor Rakesh and Professor Liu, are welcome to submit a paper to this conference. And because you are invited, you don't have to pay anything. It is free. Okay, then this community, we discuss many topics like, as I said before, PE and PE related applications, like about converters, topology, magnetic design, wide bandgap converters, battery charger, LED lighting, power system applications, etc. So many things. So this is our network. You see, we have, this is a VPEC in the middle. We have some community like IEEE, you know, IEEE Vietnam, IWJ. This is the institute in Japan, and KIP is in Korea. And in Vietnam, we have a VAA. It is a Vietnam Automation Association. Okay, and our network, we have many universities all over the world. Okay, so you are welcome to VPEC, and welcome all of you to the today webinar. Then next, I would like to focus on our presentation today. Can you see it? Okay, today we have two presentations. The first one is from Professor Rakesh. Professor Rakesh is from Denmark. He is currently working as an associate professor in SDU. I'm sorry, what is SDU? Southern Denmark University. Okay, Electrical Engineering Section at the University of Southern Denmark, Odense, Denmark. He has obtained his PhD degree in 2016 from University of Southern Denmark with the thesis titled Ultra High Efficiency DC-DC Converter using gallium nitride devices. During his PhD, he also worked as an academic guest at ETH Zürich, Switzerland. He has completed his Bachelor and Master degree from India. He has also worked as a senior research fellow at the Defense Research Development Organization, DRDO, Bangalore, India. His research interests include switch mode power supplies, application of wide bandgap devices in power converters, and high efficiency magnetic design. Okay, so welcome, Professor Rakesh. Could you share your screen and start your presentation?
Yes.
Okay, so during your preparation, I would like to remind something. Firstly, your presentation should last for 30 to 40 minutes. Then the rest will be used for Q&A. Yeah. Then as for other participants, please turn off your microphone and also your camera. Then during the presentation, if you have any questions, please type in the chat message. Chat window that I have a question. Then the session chairs will call upon you at the suitable time to address yourself, your affiliation, and your questions. Then after discussing with the speakers, please turn off your microphone again. Then please do not record anything or capture any content of the presentation, because we are also do that. And we are not allowed to capture or record anything due to the conflict of interest. Then, okay, then at the end, please remain connecting. Then we would like to take some pictures for all of you. Okay, so that's all. Please start your presentation.
Yeah, thank you so much for the introduction. So my topics, what I will be discussing today or talking about is a utilization of wide bandgap devices in various isolated DC-to-DC converters. Okay, yeah. So about me, as Drew was saying, I had my BTech and Masters from India, and then I came to Denmark for doing a PhD, and then I have some years of work experience, a few years of work experience in some colleges in India, as well as in a defense research organization in India as a senior research fellow. And then currently I'm working as a associate professor at the University of Southern Denmark. About University of Southern Denmark, Denmark is a small country compared to the whole world. But in Denmark itself, we have the University of Southern Denmark has 4 campuses in Denmark itself, and the 2 campuses which is in Slagelse, which is in Odense and Sønderborg, are more concentrated on the engineering department. So it's established in 1998 as a University of Southern Denmark, but before it was known as the Odense University. And they have 5 faculties: humanities, science, engineering, social science, health science, and we have around 4,000 employees, full-time employees, and around 28,000 students. And it is distributed into 6 cities in Denmark. So what Power Electronics department of SDU, because Power Electronics department of SDU is in 2 locations in Denmark. One is in Odense, one is in Sønderborg. Sønderborg is a location where it is in a border between Germany and Denmark. So of course we have a lot of projects between Denmark and Germany, and we get a lot of funding from this collaboration as well. So, but I am located in Odense campus, which is the main campus of SDU, or University of Southern Denmark, where the research is more on devices for DC to DC converters. We also do AC to DC converters, power factor correction rectifiers, but my expertise is more on DC to DC converters, utilization of wideband gap devices, and design of magnetic components. The degree programs we offered here are Bachelor of Electrical Engineering Technology, Electronics and Computer Engineering. But these 2 bachelor programs are taught in Danish, so you have to have a Danish language proficiency if you want to take this education. But the master's education, we have it in English. And we also provide some scholarship for non-EU students so that you don't have to pay fees if you are interested to join the masters, but you have to get into the criteria described for the entry requirement to get the scholarship. So if you're interested, you can go to the website of SDU, www.sdu.dk. So today's presentation, I will be going to an introduction, what is, and then some challenges we will face in an isolated DC to DC converter. And later on, we go to why we have to use a wideband gap devices, and then some of the practical examples of a hard switch and soft switch converter. Of course, I will explain how the converter works for the people. Maybe some of you may know about how they will work, but I just want to give you a short introduction so that everyone in the same pace. And then I will show you an optimized isolated DC to DC converter and a conclusion and some of our research project. At the end, I will end this presentation with some of our research project, which we are currently running at University of Southern Denmark. So introduction. So if you see, we have isolated. So if you have a high voltage DC bus and a low voltage DC bus, the connection between them 2 is normally an isolated DC to DC converter. Why we need to use an isolated DC to DC converter? It's mainly because of galvanic isolation. Most of the times we require, for example, if you have a renewable energy connected to the high voltage bus, or a fuel cell connected to the high voltage bus, and then we have to convert it to a low voltage usage. For example, if it is a data centers, an electric vehicle which you have to charge, or a battery bank, or a supercapacitor, or an LED lighting, anything which involves from high voltage to low voltage, you need to have, or is it almost a compulsory requirement since it need to satisfy a lot of standards. So an isolated DC to DC converter plays a very important role in this situation. So a renewable energy will be your high voltage side. It will be connected to that. It can be solar, it can be wind. And in Denmark, if you talk, it is more on wind and wind energy, because we have mainly the main contributors for wind energy production here are Siemens, Vestas, KK. So we have a lot of wind energy plants in Denmark. So, and we also have a high voltage bus line. So most of the times we have to convert it to the DC, low voltage DC bus. And here we can use an isolated DC to DC converter. And the applications can, as I said, it can be from telecommunication, DC microgrid, hybrid electric vehicles, battery chargers. So it can vary to a lot of applications in the end. So all these things required an isolated DC to DC converter. So that becomes our more requirement to have a very high efficiency and a very compact power converter. It mainly DC to DC converter. Of course, you need an AC to DC converter also. But since my expertise is on DC to DC, I will only cover the DC to DC converter part. So why efficiency becomes an important in these situations? Because as you know, efficiency is defined as the loss the input minus the P loss, the power input minus the P output by the P input, we can say, in percentage we say. And what is that loss? So if you reduce the losses is just a heat. So if you reduce the losses, we get high efficiency. So if you have high efficiency, sorry, if you have high efficiency, then you have lower heat loss, which means lower heat sink requirement. So lower heat sink requirements means we can make a converter more compact in size. So that means you can get a high efficiency converter by making it high efficiency. We can have very low losses, and this then the heat sink requirement reduces, and then we can get a compact converter. So this is a basic idea to go with a high efficiency in this converter design. Yeah, sorry. So if we talk about isolated DC-DC converters, there are various isolated DC-DC converters are available. One may be a dual active bridge. You may know that it uses a full bridge converter in the primary side and a full bridge converter in secondary side. And then it uses a transformer. So it doesn't have an inductor at the input or at the output or at the input side. So it has a transformer which normally has a high leakage inductance, or people use an integrated inductor, which is an AC inductor in series with a transformer. And that is how you can get a so this is normally a dual active bridge topology people use to get this high voltage or a high voltage to a low voltage transfer or an isolated DC-DC converter. And then later we have the boost converter topology. There it's called isolated boost because we are using an inductor in the input side. So it's just a boost converter, but it has isolation properties. So that's the reason it's called isolated boost converter or isolated full bridge converter. And here also we have the full bridge topology in the primary side, full bridge topology in the secondary side, and the transformer and the inductor. So here, the reason why we need to use this full bridge, you don't need to use full bridge all the time because it depends on the power level of the converter, because we are talking about something which is a bit more higher than 1 kilowatt. So it may be advantageous to use a full bridge topology. And then we have the buck converter, it's isolated. So the buck converter topology, we have the inductor at the output side of the converter. And the resonant converter is another converter which uses. Resonant converter is very common and it has very high efficiency you can attain with the resonance converter. But the problem is that you have to have an L and C, and this, so the highest efficiency you can get it only at the resonance frequency. So resonance frequency, they work perfectly good, and so they are very good in using. So you can see that in many of the battery charger applications or any of the where you require a high efficiency, people tend to use resonance converter a lot, a LLC converter a lot, because it gives you a high efficiency. But the problem is that that will have a high efficiency when you have a certain voltage at the input and certain voltage at the output. When we want to change the voltage, or when you have a when we want to vary the output voltage as required by the load requirement or something, then these resonance converters don't look very promising at that point. So there, people use a buck converter at the end of this converter to reduce the voltage or to change the load requirement voltage. So, but it's one of the best topology to use when you want a high efficiency converter as a for an isolated DC. If you want a high efficiency converter, the best topology to use may be an LLC converter. Then later on, you look whether you want to have a buck converter or a regulated voltage at the input side or not. So, but these are some of the topologies which we use it for an isolated DC to DC converter. But then we can talk about some of the challenges which we which we come across when we design such a converter. Sorry. Yeah. So the topologies for this purpose, since our main aim is to make an isolated DC to DC converter with a very high efficiency, we are looking a bit more into an isolated buck converter or an isolated. It's a bidirectional converter. So if you look from the other side, from the right-hand side, then it becomes an isolated boost converter. So the challenges which we face is firstly the magnetic design. So magnetic design in this case is a transformer and the inductor. So if you want to make a high efficiency converter, the transformer and the inductor design should be very good such that it has a very high efficiency. So if you make a transformer and inductor with very low efficiency, then of course your converter will not work very efficiently. So this is one of the key factors, because many of the people will make, or you use GAN or you use any wide bandgap devices as the switches to get all the advantages, but then they don't concentrate much on the transformer design. So that gives a very low efficiency at the end, because you may have calculated a lot of things, but if you don't put all the things together, then the efficiency start reducing. So just to use a wide bandgap devices will not increase your efficiency to a higher level. So you have to put effort to increase the efficiency of the magnetic. That will be the one of the highest advantage you can gain from such an isolated DC-DC converter. So the challenges will be first the design of magnetics. The second, of course, the switches. So the switches, we mean if you're using a hard switch converter or a soft switch converter, or what is the application it has to be, whether it has to be very high efficiency, whether it has to be just compact. So you have to look all these things. But then there comes the third one, which is the layout design. Because when we are using a wide bandgap devices, normally the wide bandgap devices are such that they have a low on resistance, low capacity losses, and high efficient. So this itself means that they have a low conduction and switching losses. But then if you're not using that to the extreme level or in a good level to the full extent, you don't get the advantage of this. So if you want to get the full advantage, you have to make the layout good, because that is one of the reasons. If you see wide bandgap devices, for example, low voltage wide bandgap devices from, or a high, like a 650 volt wide bandgap devices from the manufacturer called GAN Systems, or from a low voltage GAN device from a manufacturer called EPC. If you see all of them, they have a very different device or die size than compared to the normal TO247 MOSFET or IGBT, which we get in our market. So even though some of the manufacturers are making also these GAN devices in a TO247, but the reason why they are promoting this more on a die size is that you need to properly use them in your layout, such that you have a low leakage inductance, low parasitics inductance, low parasitic capacitance. So if you don't care about this layout or something, then definitely your efficiency will come down and your power density will reduce. So you have to use all these things in your converter design. So when you use wide bandgap devices, because here we are talking mainly about GAN devices, not silicon carbide, so that's the reason I am explaining like GAN devices, you really have to take care a lot. So we will talk about that wide bandgap devices in the next slide. So what is wide bandgap devices? Because I was starting from the explanation wide bandgap devices. I know some of you may know it, and yeah, you may have used it also. But wide bandgap devices is actually, they have normally the bandgap energy of a silicon is 1.2 electron volt, but for a wide bandgap device, it's much more than that. It's 3.3 or 3.4. So what we gain from this, because as a electronics guy, or we are not a proper physics guy to talk about this bandgap and all these things. But for us, what does it mean? So it means that it can come from a complete conduction to a non-conduction, or from non-conduction to a complete conduction in a very short time. And that means like they have a very high, so that means their own resistance is comparatively smaller when we use a silicon carbide or a gallium nitride, because the own resistance is dependent on the electron mobility and the energy gap. And so theoretically, a silicon carbide is 17 times smaller than the silicon carbide is smaller than the chip size is smaller than the silicon device, or the on resistance is smaller. And for example, if you want to use the same chip size, then the on resistance can be reduced by 17 times if you're using silicon carbide, or if you're using a GAN, then it is 30 times. This is actually the theoretical limit, and we have not reached the theoretical limit yet. So for silicon, we actually have reached the theoretical limit. That is one of the reasons people are looking into other devices, because silicon carbide or GAN devices are also available before, but they were used for LED applications. It's used for low power applications and RF applications. But right now, we think that, okay, power electronics or high voltage or high power applications, we can use these devices. And that's the reason they come forward. And we are we are in the very starting generation, because it's only maybe a decade we have started using GaN devices for power application. So the thing is that every day or every month they're changing their generation and new things are coming. So we have to keep an eye on it, because if you use this one time, this, like for example, this project started in 2013 and now it's 2020, and we know that there are so many changes happen. So you had to get updated with these devices, because otherwise if you started using the same devices which I used in 2013, then you won't get the same performance, because the performance or the characteristics of devices are changing every year with new generation to generation. So the next question is that, is this the only two wide bandgap devices? No, there are so many other wide bandgap devices. For example, diamond is one of the best devices to use. But since because of the cost, maybe that's not a good idea to use in power electronics. Maybe in future that will come, we don't know. So in future, some other GaN devices or gallium arsenide or some other wide bandgap device also comes into power electronics. So we should be, as a new engineers or a new designers, we should be very cautious, like which device we use and what is the new generation which will come in the future. So that is, so these devices can be used for high temperature application, high voltage application, high frequency application. So for example, if you talk about silicon carbide, they are mainly used for high voltage applications. So almost all the IGBTs can be replaced by silicon carbide device. But for when we talk about GaN devices, they comes a bit more on the low voltage side. They comes up to like 600 volt, 400 volt application, so that we can use a 650 volt or 600 volt devices. So I think in the future, because I may not be right, but we can say that for up to 600 volt applications and high frequency applications, we will stick to GaN devices. And for above like 600 volt devices or for 1200 volt to 1700 volt applications or above, we will be going with the silicon carbide devices. So that may be the trend we will see in the future, but we don't know, because there may be some changes also happening. So the only way is to just to read things about this and to know more informative and to understand a lot of these things from the people's point of perspective, from the application point of perspective. So, and of course, the high frequency, these devices are meant for high frequency applications, so you can use it for high frequency application. But the thing is that just always don't think that high frequency application means just you have to go with very high frequency, like 1 megahertz, 2 megahertz and all. But if you go with a high power level, maybe it's not a good idea to go with a very high frequency, then you have more switching losses. And this may kill your device in some other form. Of course, these are meant for high frequency, but that doesn't mean that silicon is not meant for high frequency. People use silicon for 1 megahertz application as well. So silicon can do it, but if you see the turn on and turn off behavior of a silicon device, it may be a bit slow, and that may be the reason you don't want to use it for high frequency applications. So if you are using a soft switch, it should not bother much whether you're using a high frequency application or low frequency application for a silicon device. So, and then in silicon also, if I say this wide bandgap devices is the next future, silicon devices are not dead also, because there are new silicon devices coming. Super junction MOSFET are silicon devices, which are also as good with low on resistance and low capacity losses. So if one of the big problem with the wide bandgap devices is the cost. So if you are going to reduce the cost, maybe even a super junction MOSFET can replace your circuit to have a good performance. Yeah, so we will go to the remaining portion. So the next one is an isolated DC to DC converter. Here I talk about a hard switch converter. Why we have to look into hard switch converter? Because if you know that hard switch converter is something like people don't look much into recent times. They didn't see much papers on hard switch converter. The hard switch converter is nothing, but here we have a different, because you may have heard about this phase shifted or the soft switch converters in an isolated DC to DC converter. But in a hard switch converter, what the waveform look is like that, or the switching waveform is that you turn on these diagonal switches for the first instant, that's a power stage, and these two diagonal switches in the secondary side, S21 and S22 are on, so that the power flow is from this to output. And in the second phase, so that is the first or the power stage or the power transfer stage. And during the second stage, you have none of your primary switches are turned on, so that you don't have zero losses in the primary switches at that time. So the conduction losses during that time is extensive. 0. So this is actually a good advantage because these devices, if you're using GAN devices, you can turn them fast and turn them slow. So you may not need a soft switching in some of these cases. And if your transformer is good, then you can actually, the transformer is good in the sense like you have a low leakage inductance. Because normally if you read a soft switch or phase shifter converter, you have some leakage in the transformer. And this leakage is used to do the soft switching of the capacitance in these devices, in the primary devices. And then during the second phase, that is the freewheeling stage for secondary side, we have the current flowing through the transformer. So there is a conduction losses during that time also. So you have a conduction losses. These you can avoid using a hard switch converter, but you have to be very careful that the transformer has to be good. So what we will do, we just have the comparison of this hard switch and the soft switch. And the soft switch, as I said, we use the magnetizing inductance in this case. And there are other way of soft switching also, but here we are using a magnetizing inductance to do the soft switching. So in that, you can see that you have in the second phase, you have both the devices are conducting. So you have both top switches are conducting in one phase, or both bottom switches are conducting in the primary side in the second phase. So these two topologies are very common. And this is actually one of the phase shifter converters, one of the converter which a lot of people, and if you see, you will see hundreds of thousands of papers on this thing alone. But you don't see much with a hard switch converter. But in our department, we are actually looking into a bit more in the hard switch. So as an engineer or as an analyte, and so we have to analyze this converter also, right? Because we cannot just say that, okay, this should be working high efficiency in this converter. We have to see that whether it comes to high efficiency or not. So we can actually divide this efficiency of power loss into a simple model. When it is simple, it is easy to understand. That's the reason we are going into a simple. So here the efficiency, if you want to increase efficiency or for any power converter, we can draw a power to efficiency curve. And you can see that this portion, the initial portion of the converter efficiency is actually determined by the ideal losses or the switching losses or the capacity loss. All these things are ideal losses or the core losses in the transformer and the inductor. These things are distributed from the K0, which is ideal losses. Then comes the voltage losses. For example, if you have a diode or a conduction losses from the diode, then that is dependent on the I0 losses or the output current, just the output current. So it's a straight line. And then we have the resistive losses. That comes the last. So for example, if your converter is more resistive, have more resistance, for example, if the own resistance of the converter is high, then you can see that this slope will be more towards your converter, even though the power rating is higher, your converter own resistance is higher, or the losses from the own resistance is higher. You can see this slope will be more. So some of the efficiency curve, if you look and see that, okay, they are dropping it after some point, then means they're efficient at this point, but maybe dropping at this point means their own resistance of the devices are much higher. Why it is higher? One reason may be when you increase the power, your heating losses are increased. And in that case, the heating losses increase means you have a problem that the own resistance increases with that. And then you will, even though you expect your converter to be efficient at that point, but your own resistance of the devices increases with temperature. And this makes your converter more lossy. So you will see that in the efficiency curve. So by looking in the efficiency curve, we can see that where the person has designed the converter. So sometimes you can see that some of them, so, and it depends on the application also, because in some applications, you only work on 40% load, on 40% power load, but the remaining load is actually maybe once in a while only it comes in some applications. So you have to really think where you need to put your efficiency curve. So if you have an application which required only the efficiency to be very high efficiency in the starting point, then try to reduce the switching losses or the core loss and increase the ideal, because there is always a balance. So you need to increase the other thing. Then your converter is more efficient here. And of course, once in a while, your converter has to go and then requirement has to be met, but you can make the converter very high efficient on that. So we cannot just generalize and say that, okay, make this converter for all these things. If you want the converter for certain applications, look for the application and then model the converter. So with this model, you can easily identify that where the losses are lying or where the losses are actually kept, and then you can make the converter more efficient. So then the next question is that where to choose my switching frequency? So that you just have to do with a power density, magnetic power density, I would say. and then the efficiency and the switching frequency. You just have to do trigger with this, because you can find the core loss, you can find the copper loss. I will come with that equations later. And you can see that what frequency you have to use, and then you see that, okay, so in this requirement, I need the highest efficiency. So I would say, like, if we want to get a high efficiency, I have to choose 50 kilohertz. But if I want to make a compact, very compact, with don't much of the efficiency, maybe I choose 100 kilohertz. But after some point, you can see that you won't gain much with the power density. So maybe it's better to not go with much higher frequency, because it's also hard switch converter. That's also the reason you will see, you won't benefit much from the frequency of like about 200 kilohertz. So the transformer design. So transformer design, so you can use the leakage inductance, you can use the AC resistance, you can use the DC resistance equations, Dowell's equations, and then you can actually find and then you use a high precision LCR meter to find the leakage inductance and AC resistance, and see that in our calculation and the measured value is actually quite good. So it's like 37 nanohenry for the leakage inductance. So you can see that the leakage inductance is extremely small in this type of transformer. So because we don't want to use that leakage inductance anyway, so it's better not to have that, but it's almost impossible to delete that, but you get that. But 37 nanohenry, as a transformer designer, you will see that if you're a transformer designer, you know that up to 1% of your leakage inductance is accepted. But here you can see it's only 0.0026, and you can get the calculation before you do the transformer by using these equations. So the core loss, the copper loss can be calculated by the statements equation, the basic statements equations you can use, or you can use the IGSE, the improved generalized statements equations, if you want to use if you want to get a bit more precise value. And the copper losses you can easily calculate, because you know the AC resistance, because you can calculate, you can take even from the measured value and then find the RMS value and then multiply it with that. The RMS value of the current and the AC resistance, then you get the actually the real copper loss, what we have to experience in your converter. The core loss, so it's a bit tricky, because the value you just measured or you just calculated is actually from theoretical estimations. So it may not be the exactly, but you can get a rough estimation of that thing. And of course, you have to choose the correct material for this, because here we are using a 3C95 material from ferroscube that has a bit flat core loss. If you see, for example, if you see some other material like 3C90 and all, you can see that the core loss is lower at certain temperature. So you look into the data sheet and see that which material you have to use. So here we are using a 3C95. This is a bit similar to N87 or N92, I think. Yeah, something in EPCOS before, or Philips. So the efficiency of the converter, you can just of the transformer, you can just calculate. And this, if with these losses at this 1.7 kilowatt power, it is around 99.75. So the inductor is also specially designed. It's also using a copper foil winding for the inductor. The inductor is also made in our lab. So you can use here, we are using two windings. One is an AC winding, a DC winding, because this inductor, this is a buck inductor. So you can see that they have a ripple current, which is a high frequency, and a constant DC current. So the ripple current has to go through the AC winding so that it has a low AC resistance, and the main current, that is DC current, has to go to DC winding. It won't happen completely, but you can see that there's a paper also on this thing. If you just search, you can find this type of papers, like using this two winding topology. And here the two winding topology, it gives you a bit more higher efficiency compared to a single winding topology. So you use two windings, one for the DC winding and second for the AC winding. Of course, the complete DC current or the AC current will not go to the one winding alone. There is a ratio. If you see, it's almost 1/3. Theoretically, you can estimate it also. And so you can calculate the DC winding losses and the AC winding losses. You can use the Dowell's equations or the equations in the in Carsten, in the paper from Carsten, Bruce Carsten. He has a paper on this AC winding losses, how you can find it. So you use the same principle and then find the losses in the inductor. So you can calculate the core losses from the same statements equations, and then you can find the core losses. You can find the core losses from the statement equations, and then you can find the copper losses from the AC resistance you have calculated, DC winding losses and the AC winding losses. So that gives the copper loss. the efficiency of this inductor alone is around 99.88%. So the one thing you made is that you made a high efficiency in transformer and a high efficiency inductor. Yeah, this I'm just skipping it because I don't think we have time. So the very good advantage of GaN devices, why we are going with the GaN devices, it's a isolated DC to DC converter. It should work on bidirectional, so that it's better to have a zero reverse recovery losses. If you use silicon carbide or if you use silicon devices, you have a reverse recovery losses from these devices. But for a silicon, for a GaN, we don't have a reverse recovery losses. And as I mentioned before, these devices are extremely small. You can see it's 3.6 mm into 1.6 mm dimension for the primary devices. And the secondary devices is also like 4.1 mm into 1.6 mm. So the drive losses you can calculate, the conduction losses you can calculate, the capacity switching losses, that is actually the one of the major portion of the switching losses in this type of converter, because we are talking of a hard switch converter. So of course you will have switching losses. So how you can find the switching losses? You can use the capacity losses in the devices to find the switching losses. So that is how, that is another estimation of the losses. So instead of finding the energy loss in some of the papers or some of the data sheets shows this EON and EO, but that is actually made with the assumption of a double pulse testing with that setup. But our setup may be not the same as what the setup which has been mentioned in the data sheet. So it may be also a good idea to just to find the capacity losses, because these capacity losses are anyway there in the devices. So you cannot get rid of them. So by switch, of course, by using a soft switching, maybe you can get rid of some part of that, but maybe not the full. So capacity switching loss is something you can calculate, and it depends on the converter topology. But for these type of converters, we have actually given equations which you can use it directly to find the capacity switching losses. So the converter which we are talking, it's a project from Innovation Founding Denmark, who were the funding for this one. And here we use GaN devices at primary side and secondary side, GaN devices in parallel. And the parallel GaN devices we have is 4 parallel GaN devices are used in each switching devices. Instead of each switching, we use 4. So there are a lot of challenges with that. I don't come with that. So then the optimum layout design is another important thing, because we are using a very small chip size converter. So the efficiency is another important thing. The efficiency, how you measure this efficiency, because we're talking about 99% efficiency, but who knows, we are measuring 98% or 97%, or we are measuring 100%. So we have to be very sure that what measurement we have doing is correct. So here we are using a very basic DC-DC measurement, where you are using a current sense resistor to measure the voltage across them, and then a voltage using a voltmeter. It's high precision 6.5 precision voltage meters, digital multimeters we are using here. And since it's a ratio, you can actually get a very high precision with this one. And the current sense resistors are also, we are using a very high precision with 1 ppm thermal stability. So the loss distribution, we can find these losses and then calculate it, and then you can find the losses. So the capacity losses in this case is corresponds to 0.2%. I will just skip some slides because for time being, I think we are. So the loss distribution, we can find it, and then the experiment result. So the converter looks like this. So this is a 2.4 kilowatt converter. You can see that the size of the converter is at 14.3 centimeter in length and 7.7 centimeter in width. So, and this just uses a PCB. It doesn't use a heatsink, and you can see the GaN devices here. So the efficiency, the calculated efficiency is the red one, and the measured efficiency curve is the dotted lines. You can see that the efficiency curve looks very flat, and it's above 98.5 for almost a lot of or a wide range of output power. So that estimate, and then you can see that the lines are also extremely correct. So you can clearly see that this efficiency is measured in a very high precision. So the maximum efficiency of this converter is 98.8%. So one big problem with the GaN devices is that you cannot measure the current. So how you will see that whether the current is, whether the converter is working fine or not. So the only thing which you can look is that use an IR image or infrared imaging of this and then you can monitor the devices or whether they are heating it up or not. You can see that the maximum temperature on this converter when it is at full load, that is at 2.4 kilowatt, is just 62 or 61.4 degrees Celsius only. So you can see that the converter is actually very high efficiency at this point. So the conclusion, the optimum utilization of GaN devices is one of the important things to achieve a very high efficiency. And the design of high efficiency magnetics, as I said, this is one of the important things you have to be very careful. And then the optimum layout design to achieve a ultra high efficiency. And the loss modeling, you have to find it. And then the maximum measured efficiency of this converter is 98.8. So this is actually an expanded verification of ultra high efficiency. You can see the same paper in one of my journal paper, which maybe I can also share with you, or yeah, so that you can have a look on this paper. I don't go with other things because I don't think I have time. So thank you very much.
Okay, thank you, Rakesh. Thank you very much. Could you share the screen again? Because maybe someone may, someone may want to see the slide.
Yeah, sure.
Okay. Okay, thank you very much for your very nice presentation. Then the first question may come from Dr. Nguyen from the US. Okay, so go ahead. Please introduce yourself and your affiliation and your question. Dr. Dung.
Hello, Professor Rakesh.
Yes.
I'm Jung from the Virginia Tech, US.
Okay,
yeah, I have several questions. Yeah, thank you very much for your very great presentation. Yeah, you gave us a very good picture for the GaN device and also like the future estimation for the GaN device application. Yeah, so I have several questions. So the first one, like, I would like to ask for your suggestion, like, when you work with the GaN device, you are an expert with the GaN device. So when you design the layout for the GaN device, and because the GaN device is so small, it's about 25 times smaller than the TO247. And that's why the thermal conductivity of the GaN device is quite bad. It's about like 40 to 80 degrees C per watt. It's much higher than the conventional MOSFET. So when we design the GaN device, like for the layout, like do you have any suggestions for the layout to reduce to increase the thermal conductivity or not?
Yeah,
that's the first question. Yeah.
Okay. Yeah, and maybe I will start with that. Or you have more questions, so you want to ask all the questions and then shall I answer or what?
Maybe one by one.
Okay, okay, one by one. Okay.
Yeah. Okay. So the first question, that's actually a good question because these devices are extremely small. So so if the small devices, then it's difficult to dissipate that much power. So that is one of the good reasons we are using this Starlink topology. So that if you use more devices, then the share will, if they share properly, the only way we can see that where they're sharing properly is by using this IR imaging. So if they share properly, then you have a bit more wider space. And the good thing with using a PCB for these things is that the PCB which we normally make is not the normal PCB. It's actually heavy PCB. So the PCB acts as a heatsink. So that way you can actually reduce this problems. Because in a tier 247, you can actually attach a heatsink, but in this case, we don't attach, we can attach a heatsink because I also have seen a design from another university, which they actually make some special heatsink using a copper tube and put it on the top of this small device. And that actually is very efficient compared to, but in our case, that's the reason we look for a bit more higher efficiency, then means we don't have much losses compared to the other one. So of course, it's a big problem. And it's one of the big challenging factors also, this to heat dissipation.
Okay, yeah, thank you very much. Yeah, that's also what I did here. I also play with the EPC and also gas system device. And I also put the copper bar on the top for the heatsink, but you know, like it doesn't have too much in the real case because like even though the loss of every GaN device is quite small, it's about 0.2 to 0.4 watt, but the thermal conductivity is still very bad, even though we use the 3 ohms copper thickness. But yeah, so that's why.
Yeah, but I think one thing is this, as of I understood, like because this converter, this nice converters you see, it's actually a lot of work we have done on that. And that is one thing I have to tell to people who work with GaN devices, that you may have, because in my case, I have failures so many times. At least first 1 year, I have complete failure with EPC. And everyone in my department, as well as when we go for industrial talk with a lot of people, they all say that you are too crazy to use these devices now, because you will see failures only. But then with constant, because you will find failures, you sometimes you cannot, because with a normal device you can actually see them where the failure is there, but with these devices you cannot see. So when you start working, after some time it will start working, and you can see that there is a lot you learn from that. And I don't think we can explain that in one section or something, like what are things we learned. So the only way to use is just use it. Of course you will have quite some losses from that, but to start using it, and then you will understand that a little bit more. Like, because sometimes the thickness of the PCB, how you have to be maintained and all these things, you can actually learn from that. And it depends on the where you place the device also. So that was one of the things I want to explain you in this presentation, but I don't think we have the time, like how to properly lay out this GaN devices, because we have actually made 2 types of like GaN layout, and that has extremely different characteristics.
Yeah, you're right. The layout affect a lot to the performance of the GaN device.
So that is actually, I think if you are interested, maybe you can read one of my paper which talks about this layout a lot. And that is something like it's quite interesting, because just to see a layout, how much power density you can increase with it, with this same devices, same components and all.
Okay, thank you. Yeah, I will look for it. And then the second question is like, when you work with the hard switching, yeah, you are working with the hard switching with the like 130-volt input, and you are using the EPC device with 200-volt VDS. So the margin is only 70 volts. So yeah, you are working with 50 kilohertz, so it's quite low frequency. So will it affect the margin when you go with higher frequency or not? Like when you go with higher frequency, the ring will be higher, the parasitic will be higher, so the spike will be higher, and then the margin of 70 volt will not be enough. So like, do you have any suggestion to do also for the layout, like to reduce the spike for that one or not?
Yeah, I think that's a good question, because of course this because here we are looking only in a very like, the DC bus should be very stable. That's one of the things. It should be a regulated DC bus, so it has to be supplied from a proper regulated DC bus, which is actually from a PFC. So that means you don't have much fluctuations there. Of course, when you use a bidirectionality, when you have the bidirectionality property, you may find some. So you need to use a snubber in that case to reduce that voltage. And most of the devices which we talk about this EPC, if you have looked the characteristics using a curve tracer, this device actually is not actually meant for even though they say it's 200 volt, they won't break down at 200 volt. They even break down only at like 400 to 600 volt only. So they have a different characteristics after that point, but still, like for short duration, it won't be a problem, because we actually check their voltage, breakdown voltage at using a curve tracer, and we found it very strange that they have very high breakdown voltage.
Oh, you mean the 200 volt device?
Yeah, 200 volt breakdown. Yeah, so but that is something like I don't have proof or anything to say now, but we actually had measured a lot of these things on these devices, and we are not published it because we don't want to publish anything which is maybe not it may not be correct completely, but we have to see that a little bit more before we say something. But it's a good, but of course they say 200 volt, then use 200, because if anything happens about that, it's not a, so, but this here we are using a regulator voltage supply to make sure that it won't go higher voltage than that. And of course we need to use a snapper, and we are using a snapper also.
Oh yeah, using the snapper we have a lot.
Yeah.
Okay, so and the last question is about the inductor design.
Yeah.
So can you go to that slide?
Of course.
Yeah. So for your inductor design, like you only focus on the about the core loss. You use the Stem-Mass equation to calculate the inductor loss. So but the Stem-Mass equation, they play with the AC. they didn't play with the DC. So how can you estimate DC bias effect to the inductor core loss? Because the DC bias will affect a lot to the core loss. They can like raise the core loss several times higher than the AC loss.
You mean the core loss, right? Just the core loss we are talking, right?
Yeah.
Yeah, the core loss, of course, we also aware of this DC losses, and we had a PhD student working on this core loss calculation alone. And of course, we also understood that this is actually the estimation. This is just an estimation. So we know that it may be a bit higher than what we are expecting here, maybe 2 or 3 times higher also. That was one of the values we got actually from this DC bias calculation, and that we are aware, but we think still it will not be much higher. Maybe like 2 or 3 watts, but that 2 or 3 watts won't affect our loss calculation much when we are talking about a 2.4 kilowatt. Of course, it may be higher, but this may be the value we can calculate it from this one. Maybe we have to use some other equations, but I think, yeah, as of now, we are only using statements equations.
Maybe that's the reason why the calculation efficiency is a little bit higher than the experiment.
Yeah, but I think still that we have to think that it's not much difference, right? So
yeah, I see that you calculate every portion very detailed, like
yeah,
you have
so,
every part of the loss. So
yeah, but I will
analysis.
Thank you so much. I will actually look on that like a bit more on this core loss, because still now nobody has asked that question. So, but it's a good question because we actually have looked into that. Because one of our PhD student actually worked on this AC resistance in inductor alone, and then the core loss they were actually doing this calculation, and we were also heard that like it can be 2 to 3 times more than this core loss, and then we asked her to, can you find this, how much it will be, and she didn't come up with an answer yet. So we don't know exactly how much will be that. So we didn't want to put anything which we don't know, right? So
I think Professor Kola have one paper about the DC bias effect on the inductor core loss.
Professor Kola and also one professor from Japan, because he also has something on that, but I don't know the name of the professor.
Yeah.
So that's what I understood from, but that is actually a good thing to look, but unfortunately, because we didn't, and we want to measure this core loss with the DC bias. That's one of the things we want to do it in the future.
Okay, yeah, that's all my question. Thank you very much for your very great presentation. Like we have a very good picture for the loss calculation about design of the GaN device. Yeah, thank you very much.
You're welcome. Thank you.
Okay, thank you, Dr. Zung. Is there other questions from the audience?
Yes, I do have one question. May I continue?
Could you address yourself? Then
yes,
your question.
Yes, I'm Tondat, calling from Belgium. I'm work from Thales Alenia Space. Now I'm active in the hardware design architects. So my question addressed in the switching loss that you calculated in your presentation. So for your switching loss, you use an equation which is more complicated than the normal one. Could you present it a little bit or share your information?
Yeah.
I think it's like 23, suppose.
Yeah, this one, right?
Yes.
You mean this equation? This,
yes, because normally the switching loss is calculated by the product of the voltage switching frequency and the capacitance.
Yeah, so this is instead of using, so normally you use this, so here the COSS value, that is the equivalent capacitance value of this devices were not exactly given. So the basic way is to find the QoSS there, the charge in that capacitance. And then the equations, why it is like that, I think you should look into one of my paper called Analysis of Capacity Losses in GaN Devices. I think it's called like that. It's a bit old paper, 2015, I think. In that exactly, it has been with each stages, it has been explained how this equation comes. So maybe that's the best way to, because it's actually quite a lot of explanation, like how the switching happens and each switching time, what are the capacitors are charged and discharged during that. And then we come up with a summation of all the things. And that is how this equation comes.
Yes. Okay.
So it's better to look into that paper and if you have some questions, just write to me, because all the things are explained in this paper. And I think that's the best way to explain that as of now. Yeah.
nice if you send a link to me so I can have a look on it.
Yeah, if you just write to me, then it will be easier.
Oh, good.
I can even share you, yeah, because the IEEE link or something, because yeah, that will be the great thing. Then I can just share with you.
Yeah, great. Thank you.
Okay, thank you, Mr. Maitunda. Is there other questions from the audiences?
May I ask one more question?
Yes.
Yeah, sorry about that.
No
Okay.
problem.
Yeah, just about a technique, like how do you solder the GAN, the EPC device on the PCB?
Yeah, with a pick and place machine.
Oh, use a pick and place machine.
Yeah, but
okay.
I would suggest definitely use a pick and place. Don't use with just hand soldering. You, of course, we have an oven.
Yeah.
So what we do is that use a pick and place machine to exactly place the device. Sometimes we use solder with a stencil. We use solder paste, and then put the pick and place machine and make sure that it is, because this thread between that legs, drain and source, is extremely small. So put that in the pick and place machine, and then place it on the with the PCB with the solder paste, and then bake it. Bake it extremely careful. It should not be tilted or anything, and then bake it at that temperature what they mentioned. And this is also the thing, like that will come with experience only, because 1 or 2 times we will also have failure with just tilting of the scan devices.
Yeah, thank you.
And then
yeah.
inspect that soldered one with your hand to see there whether it is tilted or not. If it is tilted, maybe try to use a hot gun to press it down, or you have to throw it at some point if it is too bad. I would suggest that, because reworking on these devices doesn't seem promising.
Yeah, because I use the hand soldering, and then I use the 100 volt GAN device, the EPC device.
Yeah.
And I always fail when I go higher than 60 volt.
But
yeah,
I would suggest don't go with hand soldering. And now they are coming with this balls, with this ball LG, like with the ball structure instead of this lane, like line drain source. They have ball structure, so that's also actually quite good. And some of the people may, because in the lab, some of the people may have experience with Intel processor or something, how they can put. So they may be the good one to use for this soldering.
Okay. Yeah. Thank you very much.
Yeah.
Okay. There are still 3 minutes. Then I would like to have some questions from my side. Yeah. Is this okay? Actually, I listed many.
Okay.
Okay. Firstly, your efficiency, 98.8% is pretty high, very high, very impressive. I just have one experience to share. I also working on DAB converter. Then I work on a 25 kilowatt 3-phase DC DAB converter. Then when I do the EMI test, we put the DC-DC into the antenna room. Then we measure the band from 30 megahertz to 10 gigahertz. Then after receiving the data, I calculate. Then when the converter work at only 2 kilowatt, then the emission into noise, into EMI noise, about 11 watt.
Okay.
Okay, and it is soft switching. And in this case, I don't know if you already consider such kind of loss or not, because your efficiency is very high, but the power rating is only 1.7 kilowatt. So I think the measurement technique basing only on DMM, digital multimeter, and you have individual 4 devices. So is this reasonable or reliable?
Because this is actually quite reliable, because we have tested this for various applications, like various power levels, and this seems more reliable than using a Yokogawa. Because Yokogawa is actually good for AC measurement, because where you don't have this, you cannot measure the DC values. But since it's a DC value, and then of course you may have the problem with the noise and all, that we are actually calibrating it before. We use a calibration method such that you can use the same sensors as at the input or at the output side, and then you see that like whether they have a variation in the voltage or which has been seen with the converter working, so that you have that calibration actually done before. So then we are putting it to the first both input and output side. So first we are actually doing a calibration to make sure that they read the same value, because if it is put at the input side, they should read the same value. And then we use this common mode noise filtration and all this to avoid any of these noise problems. So and yeah, so I think it's more reliable. Of course, there may be some other, because if we have for this, maybe like it's maybe not a good idea, but if it's a bit more higher power level, we can actually use the thermal measurement as well. You know, in a thermal chamber, you put it and then find the losses from that. So for maybe a bit more higher losses, it can be easy, because here maybe you will have some other losses which we don't find in thermal measurement. So this may be the best method to use it now.
Okay, because we don't have a lot of time, so I will skip the detailed discussion later. I will go forward to another question. I am quite curious about why you use gallium nitride devices, but your switching frequency is very low, only 50 kilohertz. Usually it is about maybe 500.
Yeah, I think this is a question I get every time. But actually that is something like interesting, because you don't need to use high switching frequency every time.
Yes, actually I'm now using silicon carbide, then at high power but not so high voltage, only 400.
And because one thing is we are using a hard switch converter. That's one of the reasons we are using 50 kilohertz.
Oh, okay.
So that is one of the reasons we are using. And then this, I said, like the main aim of this project is to make a high efficiency. If it was compact was our thing, maybe we will go with very high, bit more high frequency. Maybe, but we don't go, as I said, we don't want to go about 200 kilohertz as of now with this hard switching itself, or a soft switching also. We have seen some problems with that. And the other thing is that these GaN devices, the advantage of this GaN device is not for the switching thing alone. It's mainly for the turn on, turn off time we can reduce much high. So the losses from that we can reduce. And the capacity losses in this device are extremely small, of course. So what we get if you go with high frequency is that we actually just increase the losses in the efficiency curve in the starting point. So we are actually making the converter a bit more less efficient in the light load condition. And maybe we gain a little bit there in the output. So if you want a very flat efficiency curve, so that it can be used for all these things, it may be better to go with a very low frequency, or not very low, but 50 kilohertz.
Okay, I see. In my case, I have to run optimization, non-linear optimization to pick up the best efficient frequency for to achieve the highest highest efficiency.
Yeah, but the current ones which we are looking is actually looking at a bit more higher frequency, 200 kilohertz and all. So, so that the converter is actually made for very compact. So much, because here you can see that the transformer inductor uses a lot of space. So then next project we are looking at is a bit more making it a very thin.
Yes, I noted as well. I guess because if you use gallium nitride and you increase efficiency, frequency, you can downsizing the transformer and inductor like using planar, then integrate into the PCB, and it will be much more space saving.
Yeah, you can see this.
Stop right there. Stop right there.
You can see this.
Yes, this one. Okay. This
so that was something like, this is a current project, but I didn't have time, so.
Sure. Just one quick question, because you said that this is very similar to DAB duty bridge converter, but you pick the AC inductor into the DC side. Then you said that this is hard switching converter, but I am curious about why you have to do like this, because you have very high voltage ratio. You can change by adjusting the transformer turn ratio. Then I don't know. I don't know why you have to change the position of the inductor.
No, the one thing is that you can make a very high efficiency DC inductor than an AC inductor.
But it becomes hard switching converter.
Yeah, of course it becomes harder, but there are advantages of hard switch converter. But if you see the papers of hard switch converter, there are actually quite some advantages. One is that you don't have this conduction time, like, you know, during the freewheeling time, you don't have this conduction losses in a hard switch converter because all the switches in the primary side are turned off during that time in a hard switch converter.
Yeah, I don't quite get that.
Okay, and then the next one is that you have to use a leakage inductance here.
Yes.
Then actually you are making the transformer less efficient using a leakage inductance.
Not really.
You have you have a very high ripple actually here.
Yes, you're right.
Because of this leakage, and that is also one of the here you don't need to use a big snubber in this case.
As for snubber, I'm not so sure about that because, for example, I'm now using silicon carbide. The QRR reverse recovery of the diode is very small. Then also the COS is also very small. So even I don't use, I switch off at about 60 or 80 amperes, but I even don't use any snubber, only the DC bus capacitor. No other special snubber. And even in this case, you use gallium nitride. I think gallium nitride is much smaller parasitic elements. So yeah, I don't think you don't need you need any snubber in this case, right?
You need snubber.
You need?
Yeah, you need snubber in the secondary side, in the rectifier side, because of course the small leakage inductance with this capacitance rings in this point. So definitely you need, even in phase shift also you need this snubber.
Okay, time is up. Sorry, I'd like to talk more, but Dr. Zung consumed too much time. Thank you very much once again.
Thank you. And somebody asked about EMI-MC. We have not done anything about EMI-MC yet, but there are some other PhD students who looked on EMI-MC on this type of converter. So if you are interested, you can have a look on our publications and all, then you can see some of the details. Yeah. Thank you so much. Thank you so much, everyone.